I know it has been a while. I've been a little busy with something called my PhD, and it has been the first month of that, and it's been quite hectic. But most of that has been dedicated to reading up on the literature of the Milky Way and galactic dynamics. So today I thought I'd share my top picks of that reading. First off, let's talk about an N-body simulation. So that is basically a simulation of a bunch of particles, and when I say a bunch, I mean millions to billions of them, that all are acting under a certain force that we've implemented into the code that we're using to create the simulation. For example, gravity. If the equations of motion under this force are nice and simple, you can just straight up just put them into the code. However, if, for example, like with gravity of, billions of particles, you can't always do that analytically, so sometimes you need numerical approximations that you can put into the code and to allow things to run as close to real life as possible. So the next term is cold versus hot disks. A lot of papers that focus mostly on the stellar component of the galactic disk will refer to their disks as being cold, whereas research on the gas disk with a couple T's and C's will usually refer to their kinds of disks as hot. So in terms of the stellar disk or the cold stellar disk, the stars will orbit around the galaxy, plus the external force that's being applied to them to make them warp in the case of my work. But apart from that, there isn't really much else to consider. However, with gas disks, you've got things like shocks, turbulence, random motion, which also affect quantities and features within the disk. So that's the reason why they call them hot, whereas with cold stellar disks, they don't really interact in that sort of way, so they're referred to as cold. I should also mention that electromagnetism as well as gravity is usually considered in the case for gas disks and gas disk N-body simulations, whereas with stellar disks, electromagnetism is a negligible force, so we don't really need to consider it, only the gravity. Now let's actually get onto the papers. We've got 6 lined up, and most of them are going to be focused on the cold stellar disk. I've got my notes on all of the papers because I can't really remember every single detail off the top of my head, and I'm very sorry about that. But if you want a really informed galaxy review, we kind of need some key details and figures for me to reference that I can actually see. So let's get into it. Our first paper is measuring the vertical response of the galactic disk to an infalling satellite by Pohyo et al. We have actually encountered this paper in the past, but today we can go into it with a little bit more detail now that I've got a little bit of a better sort of baseline understanding of the field. So as the title suggests, this paper is focusing on how the vertical warp develops in the galactic disk over time in response to an encounter with a satellite galaxy. In this case, the models are based more so around the Sagittarius dwarf spheroidal galaxy, which is quite a mouthful, so we're just going to call it Sagittarius from now on. In this paper, Pohyo et al. Ran the simulation for an N-body simulation for the galactic disk, and what's unique about this paper and this research is that they've simulated multiple encounters with Sagittarius as opposed to just looking at one encounter on its own, very isolated, and looking at the response. So you can see in this figure, which is figure 1, we've got a couple of things going on. In the top panel, we've got the height above the galactic plane, so Sagittarius is height above the plane, and where z equals 0, so where we reach this little grey line over here, that is where we actually get an encounter, and it passes through the Milky Way, or at least very close by. So yeah, you can see we've got quite a few encounters, and they get they come along more frequently as time goes on. Another thing we've got over here is the dynamical timescale divided by the interval between the impacts. And the dynamical timescale is essentially the time it takes for the galaxy to respond to a perturbation. Another example would be, the time it takes for a sound wave to travel across a star. And you can see here that they've plotted this very intriguingly, but the main takeaway is that as we get closer and as these interactions get closer and closer, the dynamical timescale ratio actually goes up a lot more. They also looked at the first interaction in detail. So here we've got a bird's eye plot of the simulation of the first interaction, And on the left, we've got the results of the simulation on the left column, and the red bits are where the stars are high above the plane, and the blue bits are where the stars are below the plane. So that's actually the verticalness of the stars and the stellar distribution. To the right, we've got different components, Fourier components of the warp. So if you remember from last video, we said that the m=0 term is this sort of ring-like distortion, a bit like ripples in a pond, where these concentric rings either all go up and down like that. Whereas with the m=1 warp, we kind of cut this in half and we create an S-bend shaped warp. So only one side of the galaxy is going up and one side of the galaxy is going down. And then with the m=2 warp, that's just a bisymmetric version of that. So we've got the up and downiness going in quadrants as opposed to half of it or all of it, like with m=0. I didn't really mention this much in the previous video, but you know, technically this can go higher. You can have m=10, m=72, but we expect that these components to the warp are probably so small that you don't need to consider them. So here what they've done with this plot is that they've got the simulation here, and then they've split up what part of the warp is due to this m=0 warp, the m=1 and the m=2. And you can sort of see from the graphs, hopefully, that the intensity that they've plotted the colours at, so how rich and saturated the colours are, you know, corresponds to how big of a component it is. And you can sort of see as time goes on that it's the m=1 warp that is the most dominant piece of the warp. Following this in the paper, there is a lot more detail on the Fourier analysis, but I won't go into that. I'm gonna guess for the average viewer it would be very confusing, and it definitely was when I first viewed this paper, so we won't go into that. But regardless, I thought the paper was great stuff, and it was a really good foundational read if you really want to get into the topic and understand it a bit more. Our second paper is Galactic Seismology, the Evolving Phase Spiral after the Sagittarius Dwarf Impact, and as you can tell, we are focusing on the same two galaxies, the Milky Way and the Sagittarius Dwarf Galaxy. This paper is by Joss Bland Hawthorne and Tor Tepe Garcia. First of all, Tor has a Norse name just like me, so I thought that was pretty cool. So this paper is a development from a previous paper, I'm gonna guess by Binney and Schoenrich, given that the model that they created is the Binney-Schoenrich model. So this was a smaller simulation of, I think it was a few million or just a million particles, but one thing they couldn't really quite get right is getting the spirals in the stellar density of, not stellar density, in the stellar density or the stellar surface density. So the work in this paper by Bland Hawthorne and Tepe Garcia is to just expand on that and to, you know, develop this model a bit more, and so they did. Another thing to note is that they focused on only one interaction with the Sagittarius Dwarf Galaxy. The way that they modelled this, quite interestingly, is that they've given some initial conditions for the Sagittarius Dwarf Galaxy, such as the mass based on estimates we see from observations, which are really erroneous and very sort of, there's a wide range of masses for the Milky Way, not for the Milky Way, but for the Sagittarius Dwarf Galaxy. I had no clue, we really didn't know that much about it, despite it being like one of the closest galaxies to us. But I'm going off topic. They gave it some initial conditions such as the mass, and then after the encounter, basically the mass just drops to 0, and so it's still actually making interactions as we go through the simulation. It's just that the mass is 0, so it doesn't have an effect on any of the stars, which I thought was really cool. Now the results here are quite interesting because we can really see the development of the m=2 bisymmetric warps. And I know I said that in plural, and that is because we see in these figures, something called a kinematic density wave. So this is where the stars are clumped closer together in the spiral pattern. So the spiral pattern emerges from a higher density of stars in that area that just sort of twists out into a spiral shape. There is also something called the bending wave, which is also called the corrugated wave. It's a synonymous term, but this is where you actually see uppy downiness in the waves, which I didn't really realise until starting the PhD that these were separate things. You would think that they would be coincident with each other, so where it's clumped together is also where it's moving up or moving down, but apparently not. The bending wave is actually slightly slower than the kinematic density wave, but the equations that describe their speed and how fast they wind up in the galaxy is actually in a very similar form. So Bland Hawthorne and Tepper Garcia, essentially their research points towards the Sagittarius being the likely cause of the phase spiral that we see in the Milky Way. So it's a very similar conclusion to Pohjo et al.'s paper, but we're just looking at different aspects of the warp. The next paper I really enjoyed in particular. It is called The Milky Way's Rowdy Neighbours, The Effects of the Large Magellanic Cloud and the Sagittarius Dwarf on the Milky Way Disk by Stelea et al. And I really like this paper in particular because the previous papers have looked at a two-galaxy system, Milky Way and Sagittarius galaxy. But one of the limitations that their results have is that, there is far more to it than just these two galaxies. So in this paper, they actually focus on both the Sagittarius Dwarf Galaxy and the Large Magellanic Cloud, which I think paints a much more holistic picture of the situation, and I think it's, a really good idea to actually add as many components as you can. The Large Magellanic Cloud is slightly larger, or I think considerably larger, than the Sagittarius Dwarf Galaxy. The estimations on their mass, just like Sagittarius, is also quite susceptible to uncertainties, but regardless, in general we expect it to be much larger than the Sagittarius Dwarf Galaxy. However, it is much further away than Sagittarius as well. So taking both of these factors into account, their impact on the Milky Way's disk is actually expected to be to roughly the same magnitude. So they actually run 4 simulations: the Milky Way evolving on its own, the Milky Way and Sagittarius interaction, the Milky Way and Large Magellanic Cloud interaction, and all 3 of them combined. And what they found was that the Sagittarius Dwarf Galaxy is most likely the cause for those really nice pretty phase spirals that we see. So these were just like in the previous paper, these nice spirals. But the Large Magellanic Cloud's tidal tugging is probably what's making the larger scale m=1 warp that we see in the galaxy. I think figure 4 presents this probably the best. You can see that there are some internal, very small spirals that are generated just on their own, but that the Sagittarius Dwarf Galaxy seems to be extending them out to the edge of the galaxy. And then once you incorporate the Large Magellanic Cloud, you can see that you also get the m=1 warp that it looks as though it's sort of widened out the spirals at the edge of the galaxy. So I thought that was really neat. They also have a lot of great figures in their paper, and they do a Fourier decomposition that I found a little bit easier to understand than previous papers. This is no hate to any other researchers, I'm just a simpleton. Another unique feature that we captured in figure 2 is Sagittarius's streams of stars. This is actually a real thing, and ideally if we could understand it slightly better, we'd probably be able to understand Sagittarius better as a whole. I think all that we really know is we've got a rough idea of its mass, and we know that stars and gas are being drained out into the Milky Way as we speak. So this leads on to our next paper quite nicely, which is Tango for 3, Sagittarius, LMC and the Milky Way by Vasiliev et al. He should have put LMC at the end, because then it could have rhymed. It would have been Tango for 3, Sagittarius, Milky Way and the LMC. That would have been way cooler, but regardless. With regards to the streams, previous work has mainly focused on just only the Milky Way and the Sagittarius Dwarf Galaxy when it comes to modelling them. And that kind of makes sense, if the streams are because of the Milky Way and the Sagittarius Dwarf Galaxy, then you'd think that you'd only need to consider these 2 factors. Makes complete sense. However, their arguing is that we do need the contribution from the LMC in order to really fine-tune our results and models. For example, they argue that just considering the 2 galaxies on their own can vaguely give you the appearance of the stream, but they're missing a couple things, such as the misalignment between the leading arm stream track and the direction of proper motion of, I believe, the stars. And also in previous models, the general shape of the streams would indicate a very weird shaped dark matter halo. I believe the sort of gist is that the inside of the halo is oblate, but then the outer part of the halo would have to be prolate in order to sort of accurately model the streams, which I can't really imagine how that would work out either. So I can see the argument for trying to do some more research on this and considering the LMC. Vasiliev et al. Used these giant stars, which we believe belong to the Sagittarius stream. They also use their phase space information and their line of sight velocities in order to come up with a better model. They found that the general shape and general properties of the stream can be modeled without the LMC, but the misalignment can't be modeled. You need the LMC in order to account for that. And I think the leading arm apocenter gets overestimated if you don't consider the LMC's contribution as well, which I thought was quite interesting. Hence the addition of the Large Magellanic Cloud makes a good improvement to the models, and yeah, that kind of does make sense. They argue that their results show evidence for the LMC and Sagittarius dwarf galaxy being a major influence on the Milky Way structure. I also had a little look into the gas disk within the Milky Way, but to be honest, I probably won't be focusing on it much during my PhD, but I'd like to include my research on that anyways, and it's still good to get a holistic picture of the Milky Way as well. So our first our first paper on the gas wave, and our fourth paper today, is the galactic scale gas wave in the solar neighbourhood by Alves et al. And this was actually quite a big paper at its time in 2020, and it focuses on the Gould belt, which we thought was a ring of dust and gas that's sort of expanding at an incline to the galactic disk. So until this paper, I don't think there had been many very accurate measurements for distances to the clouds in the Gould belt. So what they decided to do was to try and update this with some more modern photometric data and other data that we've got over time. But what they found was that there is this very narrow but surprisingly coherent region, or line of dust clouds that's thought to be part of the belt, but it would render the sort of ring-like model wrong because it's not part of a ring, and it's about 3 kiloparsecs long, so it's extremely large. And yeah, if it is part of the Gould belt, its sort of presence would just disprove the ring structure altogether. It's a narrow and almost really perfect sinusoidal gas wave, which they've called the Radcliffe wave. The next paper I read, which was by Quillen et al., titled Birth Sites of Young Stellar Associations and Recent Star Formation in a Flocculated Corrugated Disk, which used backwards orbit integration to estimate the birth locations of some young stars in the solar neighbourhood. And when I say young, I mean like less than 100 megayears, like baby stars basically. They also looked at the birth heights of these stars and proposed that they were probably born in gas clouds in a corrugated disk or, a bending wave. So they found that these young stars were found between peaks in radial velocity distribution. So that suggests that they were born in a spiral arm that perturbs stellar orbits. And this does hint towards the Sagittarius / LMC being the main perturber for the gas disk as well. A couple of things in these papers did go over my head a little bit, and that is mainly because I'm not really focusing on gas disks, so I didn't quite get the entirety of it. But this is the main takeaway, and at the end of the day, the main point is that a lot of this hints towards the Sagittarius and Large Magellanic Cloud galaxies being a really important part to the Milky Way's evolution. Moving away from the hot disks and back to the cold stellar ones, we've got one last paper which focuses more on the dark matter halo aspect of the Milky Way's warp, if there is one. This one actually was a bit controversial. There are a couple comments that got made after this paper was released. So this paper is a slightly oblate dark matter halo revealed by a retrograde precessing galactic disk warp. You can see why I have my notes. These titles are ridiculously long. And this one was by Huang et al. The general consensus that we have through numerous papers is that this big m=1 S-bend shaped warp is precessing prograde to the galactic rotation, which is a really clear-cut bit of evidence that this warp is more of a transient, very dynamically evolving thing. However, Huang et al. Conclude that the precession is actually retrograde. They looked at Cepheids of up to 200 megayears, so young-ish to middle-aged Cepheids, and they made the assumption that the Cepheid age correlates to the look-back time in the galaxy. Now, I don't actually agree with this because it sort of assumes that the Cepheids, as soon as they're born, they're fixed in place and they don't actually move with the warp, which isn't what happens in real life. In reality, they actually move with the gas for which they were born. Actually, Cepheids show the prograde precession best, apparently. There is a correlation between the age of the Cepheids and distance from the galactic centre and the metallicity, which according to some comments on this paper may not have been properly accounted for, but I'm not really sure. Huang et al. Also then counter-argued that metallicity doesn't change that much anyways, so that sort of doesn't really need accounting for. Another thing that I was quite intrigued by was what I believe was bootstrapping of the Cepheid data, which I don't really know if that's the most appropriate thing to do when it comes to this kind of stuff, since we've got quite a lot of Cepheids and Cepheid samples. Surely there is enough to not bootstrap data. Basically what they did was when they were binning the Cepheids into certain bins, the bins had extremely large overlaps between each other. So you're basically resampling from a lot of the Cepheids again and again. You're kind of sampling this basically the same star multiple times, and I don't really know why you'd want to do that given that we've got thousands of Cepheids from you to sample from. Basically they just determined that the precession is actually prograde. However, I haven't really seen any other papers that come to the same conclusion, so I'm not really sure. At the end of the day, I think what they conclude is that this would indicate that the dark matter's shape is more oblate than prolate. But yeah, interesting stuff. So that concludes today's galaxy review. I hope you did learn something new, unless if you're my supervisor Paul, in which you already know all this stuff and then some more. I shall see you very soon with another video. I'm not really sure what it's going to be on, but we'll figure that out later. Bye for now.